Entropy. Entropy is a measure of disorderliness. To be specific in the exam, if asked to define entropy, you should mention that entropy is a measure of the dispersal or distribution of matter and energy in a closed system. What that means is that if you have a specific number of molecules, what are the various arrangement possibilities that you can have to actually distribute all these molecules? So certainly in the case of a gas, the molecules could be in numerous positions across the space. So hence a gas would have greater entropy relative to that of a solid, because for the solid, the particles are in an orderly arrangement and they are actually held in fixed position. Certainly, the other factor to look at is energy distribution. If you look at energy distribution in a gas molecule, then different gas molecules could actually be moving at a different speed. Therefore, you can have a range of molecules which possess a range of kinetic energies. So relative that again to solid which are held in fixed position and has restrained vibration ability will have lower number of energy distribution possibilities. Let's take a look at the 5 factors that affects entropy. So the first factor is S, which is actually your state. Gas has the largest entropy, followed by liquid, then your solid. And in actual fact, gas has significantly higher entropy relative to liquid and solid. So for example, you can see the gas, these are the entropies of gases, while in the case of solid and liquids, these are the entropies. Second factor that we look at is your temperature. Certainly, if your temperature is higher, you will have greater energy distribution possibilities. Therefore, because of that, entropy will increase. Third factor that we look at is mixing. When you have a room that's filled with only red ball, it will be fairly orderly, regardless of how you actually decide to disperse the red ball. But if you have red and black balls, and they are all mixed together, then mixing will allow there to have greater positional possibilities, and therefore mixing increases entropy. The next factor we look at is the number of particles. So like the same example that we mentioned, if you have greater number of red balls in a room, then you can make the place more messy or have more distribution possibilities relative to one with fewer number of red balls. Finally, the last factor is your complexity of molecules. We typically don't use that last factor unless all else being the same. Meaning to say, if we have to compare gaseous methane and gaseous ethane, then we have to look at the complexity of the molecule. In this case, ethane has more carbon atoms and more hydrogen atoms, and therefore has a higher entropy. Finally, these are some examples of entropy change. So when carbon dioxide solid becomes carbon dioxide gas, entropy would have increased. In the case of calcium carbonate becoming calcium oxide solid and carbon dioxide gas, entropy largely increased. The reason is because in the chemical reactions, you will now produce copious amount of your carbon dioxide. Next, when liquid boils to become gas, entropy will also increase. When ethanol vaporizes, entropy will also increase. Similarly, for the case of melting, where solid melts to become liquid, entropy will increase. In the case of NaCl, which is solid, when it dissolves in water, it becomes aqueous. So Na plus and Cl minus become two free-moving ions that can move around with great number of distribution possibilities. So entropy increase. Water at temperature of 25 degrees Celsius increase to water at 50 degrees Celsius. With higher temperature, then there's greater number of energy distribution possibilities. Entropy will increase. Graphite going to diamond will have entropy decreases, because in the case of graphite, it has delocalized electron, and second of all is that the hexagonal plane of carbon atoms could actually slide across each other in graphite, which means there are greater distribution possibilities relative to diamond, whereby all the carbon atoms are held in fixed position. Copper 2 sulfate aqueous crystallized to become copper 2 sulfate solid. In this case, Cu2 plus and SO4 2 minus, when solidified, are held in fixed position, so the entropy decreases. Gaseous iodine condenses to iodine solid, entropy decreases. Finally, NH3 gas chemically react with HCl gas. So 2 moles of gases combine to form 1 mole of solid. So obviously there's actually a big decrease in terms of number of gaseous molecules, so the entropy decrease. Now we look at the next formula, Gibbs free energy. Gibbs free energy is defined as a maximum possible work a system can do. So Gibbs free energy is equal to delta H minus T delta S. This formula you have to memorize and it's not in the data booklet. Let me give an example as to how we can use that for our calculations. Before we deploy this formula to show how we can use it for calculations, we want to highlight that Gibbs free energy and your enthalpy change has the same unit, which is kilojoules per mole or joules per mole. In the case of T, the temperature must be Kelvin. In the case of the entropy change, it will be joule per mole. In the case of the unit for entropy change, it will be joule per mole per Kelvin. In these reactions that we have, we are now provided the enthalpy of formation of sulfur dioxide and sulfur trioxide. Similarly, we are also provided the entropy of your sulfur dioxide and sulfur trioxide and as well as oxygen. In this example, we're given the enthalpy change. We're given the enthalpy of formation of your sulfur dioxide and sulfur trioxide. So from the two data, we can calculate the enthalpy change of this reaction. And it worked out to be minus 197.8 kilojoules per mole. So we can substitute this value into your delta H. It is important to take note that we have to multiply the number by 1,000 since it's kilojoule. Next, the entropy change is negative 187.8 joules. So in this case, we can substitute the change in entropy to here. And the temperature is 298 Kelvin, so we substitute to T. So from there, we can calculate and derive the value is minus 142,000 joules per mole, or otherwise minus 142 kilojoules per mole. The common mistake that students make is that they forget to multiply by 1,000 for the enthalpy change or the Gibbs free energy, since the unit given for this data is normally expressed in kilojoules per mole. So what is the significance of change in G? When change in G is negative, it means the reaction is likely to take place spontaneously and is thermodynamically feasible. And if change in G is positive, the reaction will not take place as it's thermodynamically not feasible. When change in G is 0, it means that the reaction is reversible. It is as likely to move forward as it is to move backward. So hence, if change in G is negative, it is an irreversible reaction, as all the reactant will be converted to product. If change in G is positive, it means the reaction will not move forward. Hence, the reactant will stay as reactants. Finally, let's take a look at the limitation of change in G. Change in G calculations only examine the thermodynamics aspect. It does not factor in kinetics perspective that examine how fast a reaction will take place. So a reaction with a highly negative change in G may be thermodynamically feasible, but still not able to take place because the reaction may have a very high activation energy. You may have reactions like photosynthesis, which is thermodynamically non-feasible. The change in G is positive. However, it is able to take place in the presence of light, as light provides the energy for the reaction to take place. Finally, there are 5 types of possible exam questions that can be asked pertaining to the Gibbs free energy and this formulae. The first 4 types is summarized in this table, where we know that your change in S can be positive or negative, and your change in H can be negative or positive. Based on enthalpy change and your entropy change, whether they are positive or negative, there are actually 4 possible instances. Now, these are the 4 possible scenarios that could be asked. So the last type of questions that you will get is when change in G is equal to 0. Typically, when such questions is given, very few data is provided. And the reason is because that by examining the chemical reactions, the student need to arrive at the conclusion that change in G is 0. So let's give some examples. So in these 3 examples here, you can see, first of all, they are all reversible reactions. Second of all, is that the temperature at which diamond can be converted to graphite is also at the same temperature that graphite can convert to diamond. Similarly, for the case of cis-butyrene and trans-butyrene, and finally, for the example of solid melting to become liquid, at 0 degrees Celsius, water could also freeze to become solid. So therefore, in all these circumstances, change in G is 0. Since the reaction is reversible and the forward reaction is as favored as the backward reaction. And therefore, because of that, as change in G is 0, we will then be able to work out the relationship that change in H now is equal to T change in S. And for the example given in this equation, the melting point and the freezing point is the same, it's at 273 Kelvin. So in this case, the temperature we substitute as 273 Kelvin.